Welcome to this Science Café hosted by the Faculty of Science at Carleton University. In starting this event, I want to acknowledge that many of us are guests on the land where we live, learn, and study. The people of the Faculty of Science at Carleton University acknowledge that our campus is located on the traditional unceded territories of the Algonquin Anishinaabe people. Thank you for your hospitality, stewardship of this territory, and the teachings that come from it. And I want to emphasize we're grateful for this land, the air we breathe, the water that sustains us all, as well as the animals, plants, and other living beings. These enable all our activities: research, teach, mentor, support, study, and learn. So we recognize our responsibility to our natural environment and to reconciliation with Indigenous peoples. My name is Rowan Thompson. I am Associate Dean, Equity, Diversity, and Inclusion in Carleton's Faculty of Science. I'm also a Canada Research Chair and Professor of Physics, and so it gives me great pleasure to introduce today's speaker, Dr. Shada Ipek, for today's event. Dr. Ipek has a PhD from the University of Washington, 2015. She was a research associate at Fermi National Accelerator Laboratory, the University of California Presidential Postdoctoral Fellow at University of California, Irvine. And we were thrilled to have recruited her as an assistant professor in physics a few years ago. And she's now a great part of our department, research, teaching, and supporting a great culture and place to work and live. Dr. Ipek is committed to advancing social justice in science and society. She's a founding member of Particles for Justice, which is a consensus-based, non-hierarchical group leading actions towards social justice. So for example, the strike for Black Lives that was held in June 2020. Outside of all of this, Dr. Ipek loves to run, to sew and knit, and she's a member of the Ottawa Garment Guild. Today, she'll be talking about asymmetries and symmetries in nature. Dr. Ipek, over to you.
Thank you very much, Rowan. I will start sharing my screen now. All right, yes. Let's talk about symmetries and asymmetries in nature. And I would like to start with defining formally what asymmetry means, especially what it means to a physicist. So imagine a physical system. This could be an object or some group of people or group of materials. If you make a transformation on that system, meaning if you change something about that system, but the system as a whole does not change, we call that a symmetry of that system. Maybe the easiest example is just thinking about a disk in 2 dimensions or a circle. If you rotate a circle by any degrees on any axis, you will get the same circle, right? It wouldn't change. Or really a sphere will stay as a sphere even if you rotate it. It wouldn't look any different. That's a symmetry. A circle, a sphere, a disk is a very symmetric geometrical object. For example, there's if you're a crossword enthusiast like myself, you will know that a crossword grid is symmetric across two diagonals. So if you rotate it around these diagonals by 180 degrees, you will get the same grid. And as far as I know, this is just a choice by how the crosswords are designed in North America. If you look at this beautiful tiger, you will see that the pattern on the tiger is mirrored on both sides of his face. So there's a mirror symmetry here for tiger. And we also kind of have a mirror symmetry for our faces as well, I guess, depending on how maybe your hair is divided. If you knit or crochet, you know that you will be repeating a pattern, a small pattern several times to make a larger object. And any repeating pattern is a symmetry. You have a symmetry with respect to that repeat, basically. So we are very familiar with symmetries in our daily lives. It's not just aesthetically, but for physical or maybe sometimes biological reasons as well. And symmetries the similar kinds of symmetries can show up in large objects as well as very, very small systems as well. And so here I will be comparing, for example, a honeycomb. So, you know, just a honeycomb structure that bees make. This has a hexagonal symmetry, right? And the same honeycomb structure actually shows up in graphene. Graphene is a material formed by carbon atoms, and the same honeycomb hexagonal structure is in graphene as well. And also the same carbon atoms, instead of forming a hexagonal symmetry or being in a hexagonal symmetry like in graphene, they can also form other objects with other symmetries. For example, 20 carbon atoms can form into a structure called the buckyball. So this is again just all carbon atoms in the left-hand corner, and that buckyball actually looks like a soccer ball. It's the exact same symmetric structure as a soccer ball. And you know, a buckyball is in scale. This is actually how we produce what we use to make carbon nanotubes. So this nanoscale structure has the same symmetry as a macroscopic object like a soccer ball, which I find quite interesting. And there's no immediate reason, of course, why the graphene has the same structure as the honeycomb, but it really does. So symmetries are really very important for physicists. And one of the reasons is that we can use symmetries to simplify a system in order to understand it better and understand it more easily, actually. There's a joke about physicists, and the joke is why I chose this image of a spherical cow for my talk. So the joke goes, a farmer is having problems with her cows. The cows are not giving enough milk. So the farmer goes to a physicist asking for help. Like, can you solve this problem? I don't understand why my cows aren't giving enough milk. And the physicist takes this on. A few days later, physicist comes to the farmer and says, aha, I solved your problem, but the solution only works for a spherical cow. Because since sphere has such a large symmetry, it's a very symmetric object, is kind of easier to understand. So if all of our cows were symmetrical, we would understand their physics much better. But the symmetries are not only important for simplicity or for their simplifying, in simplifying more complex systems. They're also really, they have a more like an underlying fundamental importance in the nature of physics or the physical interactions that we study. This fundamental importance was actually discovered by a great mathematician, Emmy Noether. Emmy Noether is a German-American mathematician. At the time that she finished her PhD, she weren't really given any permanent positions in European schools, even though she had stellar reference letters from great mathematicians who were her mentors. She then immigrated to the US, and she worked at Bryn Mawr College, an all-girls college in Pennsylvania, until she died. Emmy Noether realized that symmetries are related to conservation laws. For example, you can imagine the energy conservation, a system conserving energy. That's because a symmetry in that system. Another example of a conservation law is what we call momentum conservation. Momentum describes the velocity of an object. This is the speed of the object as well as direction. If an object is going at constant speed, constant velocity, that means that it's not changing speed or it's not changing its direction. We say that that object has conserved momentum. Its momentum is not changing, and conservation means just something is not changing in time. That's actually related to a symmetry. So this is the symmetry in question here is a translational symmetry. So that means that if the object is not changing velocity, it will look the same at point A, and then it will look exactly the same at point B. So the position where the object is located is kind of not important. It becomes a symmetry. So Emmy realized this or formalized this relationship between conservation laws and symmetries in early 1900s. But this idea of momentum conservation was actually around for several hundreds of years. This is actually related to Newton's laws. Newton's first law tells us that an object does not change its motion unless a force acts on it. And thanks to Emmy, now we understand this first law in terms of the symmetries of the system, basically. There are also many symmetries that are obeyed by physics laws or physical forces in nature. For example, let's think about the electromagnetic interactions. Right? We probably all know that opposite charges attract, right? What we mean is opposite charges attract each other. For example, think about taking off your hat in a cold Ottawa winter day. You probably experience that your hair wants to cling to your hat, and that's because of the electric interactions between your hat and the hair. Your hair becomes negatively charged and your hat is probably positively charged. And these positive and negative charges attract each other. But the picture doesn't change if your hair was positively charged and the hat was negatively charged. The force between the hat and the hair here is the electromagnetic force F. It is proportional to charge of one material Q1 times charge of the other material Q2. And it doesn't matter which one you call Q1 and which one you call Q2. A similar symmetry between exchanging two bodies, basically, is also the case for gravitational force. So we are on Earth and the moon orbits around the Earth, and there's a gravitational attraction between Earth and moon. And really, Earth and moon attract each other. So there's a force acting on the Earth due to moon's gravity, and there's a force acting on the moon due to Earth's gravity. And these two forces are actually equal. And that force is equal to m1 times m2. And m1 and m2 are the masses of the two objects. And again, it doesn't matter which object you call one and which object you call two. So there's this exchange symmetry. I will continue with the electromagnetic force and the symmetries associated with the electromagnetic force to build up to other symmetries that we understand about the particles, about the fundamental nature of our universe. So let's look at the electromagnetic force again. So let's imagine two charged particles. One of them is an electron. Electrons are negatively charged, so they have some electric charge that is negative. And we call this minus E. E is just a unit of electric charge. And let's think about the interaction or attraction between the electron and an anti-electron. An anti-electron is called a positron. And positron has plus E charge. So again, E is the unit of electric charge. Electron has minus E charge and positron has plus E charge. The force between these two, between the electron and positron, is minus E times plus E, right? Over the square of the distance between them. Now, these electric interactions, or this force, is symmetric under a transformation we call the charge transformation. What charge transformation does is you take all the electrons and imagine that they turned into positrons, and you take all the positrons and imagine that they all turned into electrons. So imagine this happened like all of a sudden in our universe. All the electrons turned into anti-electrons and all the anti-electrons turned into electrons. If you look at the force, if you write it as plus E times minus E, nothing changed. It's the same force, right? So this is called the charge transformation. The charge transformation takes all the minus E charges, turns them into plus E charges, and takes all the plus E charges and turns them into minus E charges. And electromagnetic interactions are symmetric under this transformation. And at this point, I want to emphasize that a system can be symmetric under one transformation and can change under another transformation. Right? For example, just look at these beautiful socks. I knitted them myself. So these socks are symmetric if you only consider their fit or your comfort. So you can wear one of them on your left foot or the right foot, doesn't matter. If you're not looking at them, you wouldn't notice that one of them is different than the other. Or maybe you are colorblind and you cannot differentiate between the colors because they are not symmetric when you consider their color, right? They have a different pattern basically. So keep this in mind when we think about the symmetries of fundamental physics. I also forgot to show you my spherical cow. I have a personal spherical cow on my desk. So the symmetries of fundamental physics, and when I say fundamental physics, I mean the physics of particles, fundamental particles like the electrons. These fundamental particles obey respect certain symmetries and transform under certain other symmetries. What we call particle physics is trying to understand how elementary particles interact with each other. And when I say elementary particles, I mean the building blocks of our universe. So these building blocks are the smallest structures in the universe. They cannot be broken into further smaller things. For example, an atom, we can break it into its nucleus and electrons, and then nucleus has protons and neutrons, and then we can break the protons into further down to its components, and those components are quarks, and we cannot break quarks into other things. So these are truly elementary structures. They cannot be broken into smaller things. They actually don't have an internal structure, but it's a bit complicated to think about them as point structures. Anyway, these elementary particles, which I will tell you about the particles themselves in the next slide, but these elementary particles themselves have certain transformation properties under certain transformations. And these transformations are similar to rotations, but they have more of a mathematical structure than just rotating a sphere, basically. And these special rotations or special transformations can be described by mathematical structures called symmetry groups. And for the standard model of particle physics, there are three groups. There's an SU3, what we call SU3. This is a special unitary group. This group describes how strong nuclear interactions work. And then there are two other groups, SU2 and U1. And SU2 and U1 describe how electromagnetic interactions and weak nuclear interactions work. If you are mathematically inclined, this will tell you a lot, or if you take it any group theory or abstract algebra. But if you don't know about groups, really think of them as very special rotations in some maybe higher dimensional space or some lower dimensional space. And the standard model of particle physics is basically, again, a combination of the elementary particles and how they transform under these symmetry groups. And let's talk about elementary particles just a little bit. So this table here is basically a periodic table of elementary particles. They are grouped with respect to their certain properties, and within each group, they behave similarly. The elementary particles behave similarly. The first group here is the quarks. Quarks are elementary particles that are inside the proton and neutron. So three quarks come together, they bind into each other via the strong nuclear force to form larger structures like protons, neutrons, and some and other larger particles. Quarks are the only particles that have strong nuclear charge. And when I say charge, you can really think about like an electric charge, but a different form of electric charge. All of these particles have certain quantum charges, some quantum properties that describe them. And the quarks are the only ones that feel the strong nuclear force, basically. The other group of particles are called leptons. The most famous lepton is the electron. Electron is what orbits around the proton in an atom, right? Electrons are electrically charged. They have a -e electric charge, and they are not charged under strong interaction, so they do not see the strong nuclear force. They interact with the proton just because proton is electrically charged as well, and they interact with the proton via the electromagnetic interactions mainly. There are two other elementary particles next to the electron, the mu and tau. So for elementary particles, we sometimes name them with Greek letters or Greek words. So mu is the muon lepton and tau is the tau lepton. And muon and tau are exactly like the electron as far as their quantum charges are concerned. They are just heavier than the electron. Actually, muon is about 200 times heavier than the electron, and tau is 10 times heavier than the muon. But other than that, other than their masses, they are exactly the same. And this is actually another symmetry of the standard model. There's a similar symmetry for quarks. For example, you see the first three quarks on the upper row, the U, C, and T. They are also only different in their masses. All of their other quantum charges are the same. Similar for D, S, and B. Their quantum charges are exactly the same, except their masses. They get heavier and heavier as you go from left to right. Each particle here, we call these a different flavor of particle. So maybe electron is electron flavored, muon is muon flavored, tau is tau flavored. Physicists are amazing name givers. And the idea that these all have the same quantum charges tells us that there is a flavor symmetry. So the natural forces that are given here, they actually do not see a difference between different flavors. And we don't know why this flavor symmetry exists. As far as we can tell, it's a perfect symmetry. It has never been proven to be violated yet, but we don't know why. And we don't know, maybe there's some asymmetry between the flavors that we haven't been able to measure yet. But as far as we can tell, it's a very good symmetry between flavors. So it's another interesting symmetric structure that describes fundamental particles. The next group of particles here are called force carriers. These are also elementary particles. Maybe the most famous force carrier is the photon. So here it is given the name gamma. So photon carries the electromagnetic force. So this is basically when you have an electron and positron, or a positively charged particle and a negatively charged particle, there's kind of a photon that goes between them to give you the electric interactions or the attraction between them. And photons are massless particles. There's a similar particle called the gluon, which is again a massless particle that carries the interaction between quarks. These are strong nuclear interactions. And this is the reason why quarks bind together to form a proton. And it's actually very hard to break a proton. That's why it took us many, many years to be able to do that. And that's why they're called strong interactions. They are very strong, actually. The other force carriers here are called the W and Z bosons. Boson is a type of particle which has a property called spin, which is an integer value. The W and Z bosons, they mediate what we call weak nuclear interactions. And weak nuclear interactions are what is responsible for nuclear decay and basically what runs our nuclear reactors, and also why atomic bombs work. And weak nuclear interactions, as in their name, they are weaker than strong nuclear interactions. The last elementary particle here is actually one of its kind. This is the Higgs boson. Higgs boson is a very special particle. It was also the latest particle to be discovered. It was discovered at the Large Hadron Collider in 2012. The theory of it was predicted to exist in the mid-1960s. It took us more than 50 years, or about 50 years, to discover the Higgs boson. And Higgs boson is the reason why the particles in the standard model, the ones that are massive, actually have mass, but it's also responsible for a very, very important symmetry breaking. And I cannot explain it in this talk, but it is actually one of the most important breaking of a symmetry in our universe, basically. And the Higgs boson is the reason for that. So it is very interesting, again. and Higgs boson is the existence of it is related to a symmetry, but more importantly, related to breaking of a symmetry, which is really important for our universe. And what is not included in this periodic table of fundamental particles is gravity. So that's the fourth force in nature. We have electromagnetic force, strong nuclear force, weak nuclear force, and gravitational force. It's just we don't know how gravitational force fits in this quantum picture. We don't know, we don't have a quantum understanding of gravity. We don't have quantized gravity. So that's why we don't usually put it, we never really put it into this picture. All right. So now we have these nice elementary particles, and I told you that they obey certain transformations, or they are symmetric under certain transformations. What is actually one of the most important transformation and symmetry in elementary particles is the idea of handedness. It is this idea of handedness is kind of a macroscopic and classical experience. So some of us are right-handed, we primarily use our right hand. Some of us are left-handed, we primarily use our left hand, right? So it turns out most people are right-handed. So I guess in our species, I don't know the animal kingdom, but for humans, most people are right-handed. So the primarily use your right hand. The right-handed and left-handed in physics and in some other sciences too, we call that chirality. So some things are right chiral and some things are left chiral. For example, you see this in DNA. So DNA has a double helix that like spirals. If that spiral is clockwise, is a right chiral DNA. And if that spiral is anti-clockwise, that will be a left-handed or a left chiral DNA. And turns out all of our DNA is left-handed. I think the proteins in our bodies are also left-handed. So there's this, even though the biology would have worked for both left-handed and right-handed DNA, it's just our everything on Earth has only left-handed DNA. This is similarly like left-handed and right-handed people, as long as I guess they don't need to use scissors, because scissors are mostly made for right-handed people, nothing would have changed. But it's just the chirality symmetry is broken somehow, and then we end up with mostly right-handed people. The idea of handedness exists actually for elementary particles too. It's a bit harder to define. It's like it's a quantum property or a quantum charge, but some particles are left-handed. For example, we have left-handed electrons, and some particles are right-handed. So we have right-handed electrons. Some positrons, these are anti-electrons, are left-handed, and some positrons are right-handed. Again, we have left-handed quarks and we have right-handed quarks. These both exist in the universe. We have left-handed antiquarks, we have right-handed antiquarks. These also both exist in the universe. The one particle that breaks this left-right existence is our neutrinos. Neutrinos are neutral leptons, so they are the bottom three leptons here. Again, they're kind of like the electrons, but they are neutral under electromagnetic interaction, so that they don't have charge. Also, so far we have only observed left-handed neutrinos. As far as we know, there is no right-handed neutrino in the universe. So there is no right-handed counterpart to a left-handed neutrino. They can be left-handed neutrinos and they're right-handed antineutrinos, but there's no right-handed neutrino or a left-handed antineutrino. So this kind of a breaking of this left-right symmetry, or this chiral symmetry, basically, just because right-handed neutrinos do not exist. Sorry, I'm sometimes mixing up my left and right. But there's also some other ways that the left and right-handed particles behave differently. Really, our universe is not left-right symmetric. This left-right symmetry violation, or left-right asymmetry, was discovered by a great physicist, Chen Xinwu. She's a Chinese-American physicist. In 1956, she was looking at decays of cobalt-60. So these decays happen because of the weak nuclear force. Cobalt-60 decays to nickel-60, emitting an electron and neutrinos and photons. And if you look at the direction that these electrons were emitted, Chen-Xun Wu showed that the electrons were emitted in a preferred direction. There was a certain spatial direction that the electrons would fly off, basically. And this is because, now we understand, it's because the weak nuclear interactions can only produce left-handed particles or right-handed antiparticles. So only left-handed particles actually feel the weak interactions. And this left-right chiral symmetry is, we call it parity. It's like a mirror symmetry. So your right hand will look like a left hand on the mirror. So this parity symmetry is violated in weak nuclear interactions. This is called parity violation. And this is why I should also say that this parity violation was proposed by theoretical physicists, and after it was discovered, the theoretical physicists received a Nobel Physics Prize, but Chen-Xun Wu was not given honor, even though she is the one who showed that it was the case, actually. This parity violation is the reason why when I was writing the symmetry group for the standard model, we put an L under this SU2 group. And L is for left-handed. Only left-handed particles see the weak interactions. So let's look at the weak interactions. Weak interactions are actually like really weird, and they're super interesting because of their weirdness. So we already established that if you do a charge transformation, the electromagnetic force don't feel that charge transformation. Electromagnetic force is symmetric under just that charge transformation. So if you take a left-handed electron, turn it into a left-handed positron, that's a symmetry for electromagnetic interactions. That's a charge transformation. But weak nuclear interactions will feel this transformation, because whereas left-handed electrons interact via the weak nuclear force, left-handed positrons do not. So that's already a major violation of the charge symmetry. And again, parity symmetry or a parity transformation takes a left-handed particle and turns it into a right-handed particle. Parity transformation is just a just taking the mirror image. So a left-handed electron turns into a right-handed electron, and the weak interactions, again, will not see a right-handed electron. So weak interactions violate charge symmetry and parity symmetry. So they're already very interesting. They are violating these like nice symmetries that are obeyed by electromagnetic interactions. We can also think about making successive transformations. For example, take the electron, left-handed electron. If you do a charge transformation, it turns into a left-handed positron. And then after that, if you do a parity transformation, just like put it in front of a mirror, the left-handed positron will turn into a right-handed positron. So now right-handed positron is okay. It interacts with the weak interactions. So weak interactions see either left-handed particles or right-handed antiparticles. So they still will feel some weak nuclear force. But it turns out, for reasons that are not clear to you now, but it is somewhat clear to particle physicists, the interactions of right-handed positrons and left-handed electrons are like a teeny tiny bit different. Even though they should be the same, there's no reason they shouldn't be the same. It just turns out they are different. And this is called charge parity violation. So weak nuclear interactions violate charge symmetry, parity symmetry, and charge parity symmetry. So they are super fun. And this is, and at this point, I've been talking about antiparticles a lot, but I haven't really formally defined what an antiparticle is or antimatter is. So let me do that before I move on to, before I move on to the next. So standard model of particle physics actually does not only predict particles or does not only deal with particles, but for each particle, there's also an antiparticle. And a particle and its antiparticle have the exact same mass, just opposite quantum charges. So electron has minus E charge, anti-electron, which we call a positron, has plus E charge. That's the only difference between them. Similarly, there are quarks, and then there are antiquarks. And antiquarks have the opposite quantum charges. 3 quarks can bind together to form a proton, and 3 antiquarks would bind together to form an antiproton. And a proton and an electron, they can bind together to form the hydrogen atom. Antiproton and positron can bind together to form the antihydrogen. And we actually can produce antihydrogen at the lab and study its properties, which experimental physicists do. And they compare the properties of antihydrogen to hydrogen to see if there's any difference between them or not. So this is like super interesting, thinking about antimatter. And antimatter is very normal for us. I used to, as Rowan said, I used to work at a national lab called Fermilab in the US. And Fermilab had a particle collider called the Tevatron. And Tevatron collided actually protons and antiprotons. And when it was working, they would produce 10 to the 10 antiprotons per hour. After the Large Hadron Collider at CERN turned on, Tevatron became obsolete. So they shut down in, I think it was 2010 or so, I forget, or 2012. The Large Hadron Collider at CERN is another particle collider, and this one is in Europe. They collide protons and protons, but when you collide protons and protons, you can produce both matter and antimatter, basically, and again, study their properties separately. So antimatter for particle physicists is nothing exotic. It is, it is very common to deal with. And one thing we know about matter and antimatter is that when they come close to each other, they annihilate. So they will just, kind of come together, combine, and then they destroy each other and turn into energy in the form of photons. This is maybe, I mean, not obvious, but if you sum minus E plus E, you get 0, right? So you kind of maybe expect that the electron and positron, they will attract each other and they will destroy each other. That's fine. But this also tells us that if there was any antimatter around us, like if there was an anti-Shada in this room with me, we will just attract each other and then we will destroy each other and we will just turn into pure energy. Similarly, if there was an anti-Earth close by, our Earth and anti-Earth would just come together and then they become 0. If there was some anti-Milky Way, our Milky Way would find each other and then they will annihilate each other. And again, we will end up with just photons, just energy. The fact that we exist, so the fact that there's, we are not getting destroyed all of a sudden, means that there's no antimatter right now in this room, and there's no antimatter around you either. I'm hoping none of you are getting annihilated right now. So that fact on its own is actually quite interesting, because standard model expects both matter and antimatter, and they behave pretty much the same, but there's no antimatter in the universe. Because we exist, that means that we did not annihilate at some early time in the universe. That means that there is no antimatter in the universe. So this is actually very fundamental in both the beginning of our universe and how structure in the universe forms. So we think that our universe started with maybe a Big Bang and after a period of inflation. And inflation is an exponential growth in space-time. And that exponential growth, the nice thing about inflation is that it makes everything homogeneous. So no asymmetry will survive inflation. And after inflation ends, we think that the universe is in a symmetric form, because that's actually the reason why physicists like inflation. So we believe that our universe started with equal amounts of matter and antimatter, but we also know that there's no antimatter now. So that antimatter should have been destroyed at some point. And we actually know when the time that it's, we know that it should have been destroyed before the universe was about a second old. Because this 1 second mark is when we start forming atoms like hydrogen, helium, and deuterium. And those, the primordial, very ancient atoms in our universe is all made up of protons and no antiprotons. So this is a very fundamental existential mystery about our universe. This is called the matter-antimatter asymmetry of the universe. The asymmetry is that there's basically no antimatter. And we actually can quantify this asymmetry as this ratio here, eta. It's called the baryon to photon ratio. Baryon is just a collective name for protons and neutrons. It It is the ratio between number of baryons minus number of antibaryons over number of photons in the universe. This can be calculated theoretically and also measured as well. And the measurement is that this asymmetry is about 10 to the minus 10. And what that number means is that that 10 to the minus 10 number corresponds to one extra quark for every 10 billion quark-antiquark pairs in the universe. So the 10 billion part of quarks and antiquarks, they will come together, annihilate, turn into photons, and then that remaining one quark, or of course there's many billions of quarks, but those remaining quarks will then go ahead and form protons and neutrons and stars later. So this is the type of asymmetry. It's like a very, very tiny asymmetry, actually, just like one extra quark for every 10 billion pairs. But that asymmetry is really important because if we were fully symmetric, then all the protons and antiprotons would have annihilated with each other, and we would have no stars, no planets, no nothing. We will just have photons. And the theoretical work behind our understanding of this matter-antimatter asymmetry of the universe was done by a great Russian physicist, Andrei Sakharov. And I want to honor Sakharov here because Sakharov was actually the founding father of the Russian hydrogen bomb. But after he observed the after effects of the atomic bomb at the end of the Second World War, he absolutely deserted that effort, and he dedicated his life to peace. To peace on Earth and anti-proliferation specifically. He was exiled, he was imprisoned by the KGB, and because of his peace work, he was awarded the Nobel Peace Prize in 1975. And he was very important for anti-proliferation treaties between Russia and the US. So anyway, he's one of my physics heroes. Oops, sorry. Right, so the one thing we know from Sakharov's work and the question of matter-antimatter asymmetry is that the standard model actually cannot explain this asymmetry. So if we only have the standard model of particle physics and our universe, we expect almost equal numbers of quarks and antiquarks in the early universe, and then they come together and they annihilate each other, and then you wouldn't get any structure. We wouldn't be here, really. The reason that the fact that we are here is because there's an asymmetry between matter and antimatter, and there's no antimatter in the universe. There's no antimatter left in the universe. But we do not understand why this asymmetry exists. From the point of standard model, this asymmetry should not exist. And in order to explain or produce this asymmetry, we actually need some new physics, maybe new particles, maybe new forces. And this question, the matter-antimatter asymmetry or producing a matter-antimatter asymmetry is one of the big parts of my research program. And I don't want to take too much of your time, but I want to tell you about, very superficially about one of my ideas about producing this asymmetry. One of the new physics hypotheses or models that I introduced was, what if there was some new type of elementary particle, and this elementary particle maybe can turn into its own antiparticle? For example, initially you have a bag of these new particles, and then after some time, some of these particles turned into their own antiparticle, and then you have now a mixture of matter and antimatter. Actually, similar physics exists, or a similar phenomena exists for larger particles in the standard model. These are particles similar to the neutron, basically. And this observation received a Nobel Prize in 1980, but it doesn't happen for the fundamental particles in the standard model. So this new particle is a fundamental particle that maybe we haven't discovered yet, and it can turn into its antiparticle. Turning into one's antiparticle is called particle-antiparticle oscillations. And this doesn't necessarily produce an asymmetry, because let's say you have a bag of 5 particles and 5 antiparticles, and then after some time, the particles turn into antiparticles, but then antiparticles could have turned into particles as well. So you still have 5 particles and 5 antiparticles. So you start with a symmetric system, you end up with a symmetric system. So the oscillation itself doesn't actually violate this particle-antiparticle symmetry, right? What you need to get an asymmetry is actually, you actually require some CP violation, again, this charge parity transformation violation, because that charge parity violation translates into a case where an antiparticle turning into its particle is just a bit easier than particle turning into its antiparticle. And really, this, the picture that I'm describing is the spherical cow model of these oscillations. These oscillations are actually quite complicated, and they become more complicated in the early universe. So you can't just rely on these hand-wavy arguments. You need to do very involved calculations, and these calculations require some numerical tools like computers and computers to solve differential equations, because pen and paper is not enough at some point. And also in the early universe, our universe expands, and you need to account for that expansion as well. And on top of that, these new particles will be interacting with other stuff in the cosmic soup, and those interactions affect this quantum phenomena, the particle-antiparticle oscillations too. It is super fun. It can be done. And this is what I did with one of my collaborators a few years ago. And we looked at how we can produce a matter-antimatter asymmetry, starting with these particles and antiparticles in the early universe. So this plot is just showing you that you can produce an asymmetry. You can, if you want, you can only focus on these blue lines that says matter-asymmetry. This is the asymmetry that we observe basically. And we showed that if these new hypothetical particles exist in the early universe, they can produce a matter-antimatter asymmetry, and kind of easily actually. And these new particles their mass is about the mass of the Higgs boson. Their interactions are a bit less common, so that they are harder to discover at the Large Hadron Collider, but it can be done. So these are new hypothetical particles that we can either discover or rule out at our particle physics experiments, basically, which is super interesting, or super fun to think about. So this is one of the new physics ideas that I worked on to explain this asymmetry. There are many other ones. There are several models from me and my colleagues, but this question of particle or the matter-antimatter asymmetry of the universe still persists, and we don't know the physics behind it yet. And I will end here by thanking my my group. So this is a picture of my current and past students, grad students and undergrads. I would also like to acknowledge NSERC, National Science and Engineering Research Council of Canada, and Arthur B. MacDonald Institute for funding my research so that I can think about the matter-antimatter asymmetry.
Thank you, Shada. Very interesting talk, and I love how you wove in some of your own knitting patterns into it. That was great. I just want to invite the audience now. We're happy to go to questions. Could you please use the Q&A function? There have been a few questions posted already, but if you put your questions in, then I'll ask them of our speaker. So the first question, thanks, Ron, is just asking about black holes. So, you're talking about this matter-antimatter asymmetry in the universe. Do black holes have a role to play in this? What can you say about that?
Yeah, so it's a very good question. So one thing that we know about black holes is actually they destroy any knowledge of what went into them. So you wouldn't know if they were made out of matter or antimatter, because as soon as whatever produced them collapses, that becomes a black hole, and you don't know that information anymore. So a good question though, yeah. So yes, they could have been made out of all antimatter. It's just we wouldn't know, and they don't affect us now. But then the question becomes, say there was equal numbers of matter and antimatter, and let's say all the antimatter just formed a black hole and just disappeared, but why didn't the matter form a black hole in the same way, right? So this is still an asymmetry, basically.
Okay, thank you. So you talked about that the Higgs boson was responsible for an important symmetry breaking, but you said you weren't going to say too much about it. Can you say a little bit more? There's a question about that.
Yeah, so this is actually kind of related to this other idea that physicists love, is that at very high energies, we would like to think all the forces to unify and become together. And maybe there was some some unique source of like one source of producing all the forces in nature. And this actually kind of happens for the weak nuclear interactions and the electromagnetic force. This is called electroweak interactions. And the Higgs boson basically breaks that symmetry, that nice one symmetry, and then produces or gives us the separate weak interactions and electromagnetic interactions after below some energy scale, basically. I don't know if that answers it, but it is super fun and important.
And you gave a picture of the standard model of particle physics in terms of different particles and talked about these different parts, but you explicitly acknowledged that gravity was not in that picture. Do you think that represents one of the biggest challenges going forward?
It definitely does. I know, it definitely does. It's just, so there are ideas around to how to include gravity in this picture, like the quantizing gravity, loop quantum gravity, or maybe some form of string theory. It's just we don't know yet. It's so frustrating in a way, and I think that will probably be one of the biggest discoveries in particle physics when it is hopefully done finally.
Okay. Well, I'd just like to say on behalf of everybody, thank you for your lively and very engaging talk and the beautiful images you used. I love the spherical cow. And I invite everyone present to check out our carleton.science.ca for future events. We hope to see you at future Science Cafe events. And thank you for your attendance here today. And with that, we'll close.